All right, howdy class, welcome. This is our first recorded lecture for the semester, one of many. So we'll see how this goes. Uh, just wanted to reiterate some information from our lecture on Wednesday. So this is all of the important information that you have pertaining to our course site. It is all found on the syllabus except this part down here. Your IA and your SI leader information, but that will be found on eCampus. So these are all very important pieces of information for you, so you should write them down, make sure you know where to find them so that you can take advantage of all your resources. So Nick and Austin are there to help, but you should take advantage of them. They're really great. They know a lot about Chem 119. They've been through it themselves, so you should definitely ask them for help if needed. And always you can ask me as well. All right, just to go over some of these announcements, reminders again, Chem 119 labs start the week of the 31st. You don't need to purchase the lab manual or electronic course site until then. You won't be able to find our course site until then, so don't worry about it. You should also, if you haven't already, go on to our Chem 119 course site on eCampus and read the syllabus and the following two documents for getting started. So those are Getting Started with ALEKS and Guidelines for Using Reef Polling. So Getting Started with ALEKS will help you register for the ALEKS homework system, where you will also find the ebook for the class. And reef polling is how you will be getting participation points in our problem sessions. So make sure you have subscribed or purchased a subscription to the Reef iClicker app so that you can use that app during classes. All right, so also we have an introduction assignment due on the 28th, which is next Friday. A lot of you are already getting started or done with that, which is great, but for anybody who hasn't yet, that's fine. It will be due on next Friday, and that's on eCampus. You go to the participation questions section in eCampus, and then you'll see introduction assignment, and instead of just reading that paragraph, to submit the assignment, you want to click where it says introduction assignment. It's actually a link that opens a folder that you can put your files into. Also, your first homework assignment on ALEKS is going to be Chapter 1 homework, and that's going to be due on Sunday, the 23rd. So in order to get to that homework, you'll have to finish the ALEKS initial knowledge check first. That initial knowledge check is not graded. Do not worry about how you do, but please try your best so that we know where we're starting from for this semester as far as your prior knowledge of chemistry. After you finish the knowledge check, the Chapter 1 homework assignment will show up on the left side of your ALEKS homepage, and you can then start that. It may be under it may be in a section that says Start My Path. That's where your assignments will show up. So complete that by Sunday at 11:59 p.m. All right, so let's get into some more content about our course. So what are we going to be learning in this chemistry course? We're going to be learning about atoms and ions and molecules, learning about reactions, different states of matter, all of this. And how are we going to do that? Well, we're going to start by recalling factual knowledge. So you will read your textbook and you will try your homework, and that will give you some factual knowledge, some definitions of these different things, some different concepts to remember. Next, you're going to demonstrate understanding by completing your homework and answering the brief questions in class. Then you'll apply your knowledge to solve familiar problems and new problems. And that will be probably on the quizzes and exams. So your homework problems will be a certain level of difficulty, and then exam questions might be more difficult, but you'll apply the same knowledge that you had during the classes, during lecture sessions, to your problems on exams and quizzes. And finally, analyzing your results, that kind of just means you're going to have you're going to reflect on what you've learned throughout the whole semester. All right, so how do we learn chemistry? So during these lecture videos, you should be taking notes. Don't just watch these videos and expect to absorb all of the knowledge. Please take notes. And those will help you answer the participation questions, which will be on eCampus and will pertain to this video lecture and all following video lectures. Then during class time, you should solve the reef problems, get your participation points, and ask any questions that you have. Don't just wait and struggle. The longer you wait and don't get an answer for your question, the more behind you're going to get in the course. So don't wait. Ask questions as soon as you have them. If anything's confusing, ask a question. I don't mind. I'm here to answer your questions, and I know that everybody learns differently. So things that I say might sound like complete gibberish to you. So I try my best to teach things in a way that is accessible for everyone. But sometimes that doesn't work, and I would love for you to tell me that you are having problems instead of just struggling in silence. And then outside of class, you should be reading your textbook, reviewing problems from the lecture sessions, and doing your own homework problems, as well as going to office hours or asking for help in any other way over email or whatever. All right, so why do we want to learn chemistry? So chemistry is called the central science, and that's because chemistry is important and required and related to all of these different things. So whether you are pre-med, you want to be a doctor, you are in like wildlife studies, or zoology, you want to work with animals, whether you're an engineer, civil engineer, industrial engineer, mechanical engineer, chemical engineer, whatever, you're going to use chemistry. All of you will. Same with if you're like a geologist or studying physics and astronomy, studying meteorology, whatever, as well as if you're studying materials, if you want to learn material science and work with different types of materials like semiconductors and things like that. All of these things use chemistry. So chemistry is central to all of these other sciences, and that's why we need to learn it. And it's also pretty cool. So you'll see, we'll learn a lot of interesting things that will apply to all of your different interests. I'm sure you all come from different backgrounds and are studying different majors, so I'll try to find things that are interesting for all of you. All right, so let's talk about scale a little bit. So chemists observe systems and try to understand events at the molecular level that are responsible for observed properties or changes at the macroscopic level. So this is a pot of boiling water. The liquid water in the pot is in liquid state, so its molecules are close together, but still moving around in a fluid motion. Whereas the water vapor that's rising as steam out of our pot is a gas. Those molecules are more spread out. They are free flowing in the air. They don't have really a confined volume. And we don't think about it that way when we're boiling a pot of water, but chemists do. Chemists think about things this way. So we want to know what things at this level are causing the things at this level. So what things on the molecular level are causing the things on the macro scale. So Here's some different definitions and a scale for you. Macro scale is anything that is viewable with the naked eye. So the Empire State Building, really, really big. It's like a kilometer tall. A person or a piece of paper are, you would think they're really on the same magnitude, but they are the same order of magnitude in size, about a meter, or in the case of a sheet of paper, it's like maybe 0.3 meters long. Those are all still viewable by the eye, macro scale. The width of a AA battery, the thickness of a CD, that's like a millimeter in size, still viewable by the naked eye. But then when we start going smaller into the plant cells, bacterial cells, virus cells, these are viewable with a microscope, so we call them microscale. So now we can't see them without a microscope anymore. Can't see the germs all over us unless you have a UV light, but that is still just kind of seeing them bulk-wise, not seeing them individually. So you need a microscope. And then when we go smaller to individual molecules or even individual atoms, we're on the nanoscale or the atomic scale. And your text calls that the submicroscale or submicroscopic particles. And these are viewable with an electron microscope, and they're on the order of the size of individual atoms or molecules. So we can see individual strands of hair, correct? But if we use an electron microscope, we can make them look huge. So this is a strand of hair under an electron microscope. A typical average width of a strand of hair or diameter of a strand of hair is 100 microns or micrometers. So that's a tenth of a millimeter. So we can't really see it that well without a microscope. And then these over here are red blood cells, and these over here are individual molecules. So they are super, super zoomed in with a really awesome electron microscope. These things all look like they're kind of the same scale, right? But it all depends on these scale bars. So 10 micron scale bar versus a 5 angstrom scale bar. So that's why units are super important, and that's what we're going to talk about next. Actually, that's what we're going to talk about later. First, we're going to talk about the scientific method. So the scientific method, you've probably heard it before. You've probably used it even though you didn't think about it. But what it is, if you need a refresher, is we start with an observation or asking a question about something that we have observed in nature. We want to know more about it. We want to know why something happened. Then we make a hypothesis as to what the behavior was or how different variables are related. We make our hypothesis, and then we test it with an experiment, and we collect and analyze data from our experiment, which we use to confirm whether our hypothesis was true or whether our hypothesis was false. And if your hypothesis is true, you can propose a theory about why those variables are related the way they are and report those results. If your hypothesis is false, you can also propose a theory, or you can go back and make a new hypothesis and start the process over. So that is the scientific method. Let's see it in practice. All right, the scientific method starts with an observation. You observe that chefs always add salt to the water before boiling their water to make pasta. So you make a hypothesis. It's a best guess about your observation that can be tested with an experiment. You hypothesize that salt causes water to boil faster, so you can eat pasta sooner. So you want to see if more salt equals faster boiling time. Your hypothesis is followed by experiments. You set up a set of experiments. You boil some water without any salt. You boil some water with a teaspoon of salt. You boil some with 3 teaspoons of salt, so on and so forth. And you use a stopwatch to time how long it takes for the water to boil. And that time, those different times for boiling, are the data that you collect for your experiments. So your data reveals a number of different facts about boiling water to make pasta. After the experiment and data collection, you can propose a theory. So a theory is an explanation of the experimental results. Your theory is that the more salt you add to a pot of water, the faster it will boil. But on a practical level, do you really want your pasta to be that salty? I don't know. So probably not. So you learned something about this process, and it can inform your decision on whether or not you're going to add more salt to your pot when you boil water to make your pasta. Theory cannot be proved. So this theory cannot be proved, but if it is something that can be proven, if there's a proven relationship between variables, like Newton's laws of motion, where one motion has an equal and opposite, or an action has an equal and opposite reaction, that is a law and it is proven. We have the numbers and the experience to back it up. And then whenever you're happy with your theory, you want to report your results to someone else. Each scientist only addresses a small part of a large problem. So we have to report our results to other scientists. And the way that we do that is scientists submit their findings to journals, which use the peer review process for evaluation. So that means that editors look at your articles, and peer reviewers read the article and they might test the experiments themselves to see if they agree with your results. And if the article meets standards based on those peer reviews, then it will be published. So there's a lot of things that happen between the experiments and the journal article coming out and being blasted on Twitter. And then this is just another example of the scientific method. This is in your textbook. It didn't come out too clearly on here, but this is about smallpox. So there was an observation that milkmaids don't contract smallpox. There was a hypothesis made that said that having contracted cowpox means that you have a natural immunity to smallpox. And then an experiment, which is not really ethical, which may not be allowed in today's society, is intentionally exposing a healthy child to cowpox and then to smallpox to see if they contract smallpox. Because the child did not contract smallpox, the immunity to smallpox seems to be a result of exposure to cowpox. So that is their theory. And in order to make that theory well known, they reported it to other scientists, and in order for it to be useful in the medical community, many more humans have to be tested to confirm the model. So that is the case for the smallpox experiment.